Hello everyone, I'm Meng Yunzhou from Fudan University. Today I'm going to introduce our system, Polygon, a quick-based CDN server selection system supporting multiple resource demands. This is a joint work with Tiancheng, Yang, and Xin from Fudan University and Junjie from Huawei. CDN, Content Delivery Network, is a kind of bridge between services and users, aiming to speed up loading times by catching size content in multiple geographical locations. For example, if we want to visit the website hosted in the US, we can talk directly to a CDN server in China, which allows for faster content delivery. Many companies provide CDN services, such as Cloudflare, Akamai, and Fastly. But with the booming application scenarios, is the smallest geographic distance enough? Let's take a look at an example. Here, we have three CDN servers, A, B, C, located in three regions. Now, there are two bursts of popular CDN requests near server B. One is an NBA moment video, and the other is the widely used JavaScript library. So, according to the geographic distance, the CDN requests from North America will be all directed to server B. But such scheme will cause server B to exceed the load, especially bandwidth, which result in high average job accomplished time. But in fact, video requests are prioritized for bandwidth, not latency, and server A and server C are not fully occupied. So if we just redirect 20% of the video requests to server A or server C, the average job accomplished time for both requests will be reduced, although server A and server C have a higher latency to clients. This example demonstrates that the bandwidth load of servers also matters for the CDN selection. So besides bandwidth, what about other resources? In our paper, we have defined three types of requests sensitive to three common resource types: delay, bandwidth, and CPU. We found that each resource shows the most significant influence on its corresponding type of requests. This finding motivates us when considering the CDN server selection. We should not only consider geographic distance, but also consider the resource priorities of the request, which has a greater impact on the CDN selection. Some previous work also considered the combined effect of multiple resources, but these proposals still had two shortcomings. First, they treated the resource priority of different types of requests as the same. However, as mentioned before, their priorities are different. Second, they both are based on Anycast routing. Anycast routing loses precise control over the CDN allocation, which result in poor performance. So here we propose our system, Polygon. The key store of Polygon is the deployment of a set of dispatchers at strategic network locations. The dispatchers are responsible for resource status collection, server assignment with multiple resource demands, and forwarding requests to suitable CDN servers at a small cost. Next, let's see how Polygon works. There are 4 steps. Step 1. Collecting real-time resource status. Polygon is to periodically collect resource status and store them in dispatchers. For the resources related to the network, like delay and bandwidth, Polygon estimates them in an aggregated way. Step 2. Sending request and selecting server. There are 2 components. First, the client appends the resource demands by using the metadata in Quick. Second, Polygon designs a DRA algorithm for assigning suitable CDN servers. Next, step 3, forwarding request to suitable server. To handle the field responses, Polygon introduced the redundant forwarding mechanism. And since cross-region forwarding is usually costly, furthermore, we built an overlay network to ensure quick forwarding among dispatchers in different regions. Last, step 4, establishing unicast connection and content transmission. Polygon can directly transfer the anycast connection to the unicast connection by leveraging connection migration in QUIC. And if redundant forwarding is triggered, the client will abort the response arriving later. Polygon makes use of the advantages of QUIC. QUIC is proposed by Google to reduce the latency and enhance stability in mobile scenario. First, Polygon leverages the metadata at the handshake packet, which both supports the predefined classical resource compositions and customizable demand ways. Besides, Polygon can establish the zero latency connection to dispatchers with the help of zero RTT in QUIC. Last but not least, Polygon eliminates the real connection between client and server after CDN selection. Connection migration in QUIC guarantees the flexibility of the continuous connection, even when the IP address changes. That means only one QUIC connection can accomplish sending, forwarding, and transmitting. For the design and the implementation details, please refer to our paper. Here, we conduct an evaluation of our prototype Polygon on Google Cloud. First, we present Polygon's potential in reducing job completion time. In the left figure, compared with the DNS-based solution, pure anycast-based solution, and the faster route, Polygon achieves less job completion time in terms of either the mean or median value. We further investigate what types of requests promote Polygon's advantages. From the right figure, we observe that overall improvement benefits from each type of requests. Especially for bandwidth-sensitive requests, Polygon displays a 55% reduction, about 71 milliseconds. In addition to reducing the job completion time, Polygon can also improve the resource utilization efficiency on the server side, which can further cut down the cost for the service providers. From this table, Polygon shows a significant improvement both in terms of the number of requests completed in the same 2 hours and the average resource cost to complete per request. That's because Polygon makes better use of the unoccupied servers and alleviates the resource preemption in clouded regions. And according to our results, 64% of CPU-sensitive requests and 34% of bandwidth-sensitive requests are redirected to other regions for better performance. So, to conclude, our work found that requests in different application scenarios would have different resource type priorities. And motivated by this finding, we proposed Polygon, a QUIC-based CDN server selecting system supporting multiple resource demands. And it shows a significant improvement in job completion time and resource utilization efficiency compared with existing solutions. At the end of my talk, I will be happy to take questions. Hello everyone, welcome to our technical details report. Our work is Polygon, a quick-based CDN server selecting system supporting multiple resource demands. There are the three main contributions of our work. In summary, motivated by the priority differences of different requests, we propose Polygon, a quick-based CDN server selecting system supporting multiple resource demands. And it shows a significant improvement in job completion time and resource utilization efficiency. In the beginning, let's review the Polygon design overview. Followed by the 4 steps, Polygon can help the client choose the appropriate CDN server meeting the resource demands. For the detailed workflow, please refer to our paper. However, there are several practical challenges when we design Polygon. First, the diversity of resource status. There are numerous number of link status in every segment. It is impossible to measure the end-to-end links between all these client-server pairs. Second, effective demand delivery and robust selection. Since Polygon both supports classical resource demands and customizable resource demands, we are faced with the design challenge of realizing these two functions effectively. At the same time, the CDN allocation should be robust with dynamic network environments. Third, extra delay for connecting and forwarding. The extra delay introduced by Polygon includes the delay of reaching the dispatcher, request forwarding, and re-establishing the connection between the client and the CDN server. Now, let's talk about the first challenge, how to collect the resource status. We collect 3 types of resources: delay, bandwidth, and CPU. For the 2 network-related resources, delay and bandwidth, we use an aggregative method. That is, use a representative agent in each area to represent the status of all servers in this area. Since Polygon deploys a series of dispatchers worldwide, we use one dispatcher in each region to act as a representative agent. For CPU, it can be collected by each server. Its calculation is the ideal rate multiplying the number of CPU cores and then multiplying the CPU clock frequency. We collect delay information every hour, bandwidth information and CPU information every 1.5 seconds. Then, let's introduce resource demand information delivery. Polygon uses metadata in QUIC to bring the resource demand information. Since QUIC is a newborn protocol, we will first demonstrate the usage of metadata in the handshake process. As shown in the left diagram, Polygon uses the metadata in the client packet, and the client is set during the handshake process. For the specific metadata design, Polygon provides 2 options: the predefined classical resource composition and the customizable demand width. For the classical resource composition, such as only bandwidth-sensitive requests, like large file downloading, we predefine a set of resource compositions by assigning each type a positive integer. For example, when ID equals to 1, it means that this request only demands delay and has no requirement for other resources. In the case of predefined situation, all attributes in the metadata except the ID do not need to be transmitted because the server has stored the corresponding weights. We also allow a client to have customizable resource demands. To achieve this, the resource composition ID should be set as 0, and the flag field and the weight field should be set with detailed resource demand information. Each flag byte corresponds to a given resource type, and each 8 bytes are the weight. Considering the transmission efficiency, the client just transmits the weight block of the resource type with the true flag. We provide an example here. In this example, 30% of the weight is delay, 20% of the weight is bandwidth, 10% of the weight is CPU, and 40% of the weight is loss. Once dispatcher has received the request, they will calculate the server score according to the metadata. There are two aspects that determine the server score: the amount of currently available resources and the maximum capacity of resources. Then, to avoid the potential shape capacity degradation of the optimal node, we introduce a redundant forwarding mechanism. Dispatcher will pick up the optimal and the second optimal service and forward the request to both of them. However, we will trigger the redundant forwarding when there's no much difference between the two nodes. The second optimal service score should be 10% less, and the RTT value is 30 milliseconds shorter than the optimal service. The last challenge is reducing the extra delay. Polygon adopts 3 advantages of QUIC to solve this problem. First, Polygon leverages the zero RTT feature of QUIC to realize the zero latency connection establishment to dispatchers. Zero RTT is implemented based on the forward secret key. Once the client has ever connected to the dispatcher, the forward secret key between the client and the dispatcher will be kept, and this key will be reused in the next connection. The frequent interactions between the client and the dispatcher provide an opportunity for the zero RTT handshake. Subsequently, considering the high latency of cross-region request forwarding, we construct a fast forwarding overlay network connecting the dispatchers. By this overlay network, requests can quickly reach another region. Furthermore, the connection migration function eliminates the real connection operation between the client and the server. Connection migration realizes the transfer from one node to another. Universally unique identifier, called UUID, is a unique identifier of the connection instead of 5 tuple in QUIC. UUID guarantees the continuous connection even when the IP address changes. So, the server can continue the subsequent data transmission instead of re-establishing a new connection. Finally, I will show the configuration of our experiment. For the test bed, we deploy a dispatcher and a CDN server on each of 5 continents. The clients are deployed in 10 Google Cloud data centers, 3 in Asia, 3 in North America, 2 in Europe, 1 in Australia, and 1 in South America. All machines, including clients, servers, and dispatchers, share the same setting. We simulate the evaluated requests. For the delay-sensitive requests, we call the home pages of Alex Top 500 sites and generated visits to these web pages. For bandwidth-sensitive requests, we generate a video request with a size of 5 MB and visit it 10 times. For CPU-sensitive requests, we perform 100 random queries in a database with 1 million entries. We construct the evaluated requests by randomly selecting the 3 types of requests with the ratio of 4 to 4 to 1. That's all of technical details report. If you are interested in our work or have further questions, please feel free to contact me by the following email. Thanks for your listening.